Every single time you click a mouse, swipe on your phone, or stream a video, there's one little thing at the heart of it all: the CPU. It's the engine of our entire digital world. So today, we're going to trace its incredible history, from just a wild idea to the literal brain of modern life. Take a look at this. Yeah, it's an Intel Core i5, but it's so much more than a chip. It's basically a microscopic city with billions of tiny switches all etched onto a little sliver of silicon. This little square is the result of over 70 years of nonstop innovation. So the big question is, how did we get here? How in the world do you go from a concept, just an idea floating around, to this incredibly complex piece of tech that has completely changed, well, everything? All right, to get there, we have to go way back to a time before CPUs were even a thing. The very first computers, like the famous ENIAC, were these massive beasts with one huge problem. They were fixed program. If you wanted it to do a new task, you couldn't just open an app. Nope, you had to physically get in there and rewire the whole machine for every single task. Then came the big breakthrough, an idea from the brilliant mind of John von Neumann: the stored program computer. The idea was totally revolutionary. What if the instructions, the program, could be stored in memory just like the data? It meant a computer could switch jobs just by loading a new program. That one concept, it's the foundation of every single CPU we use today. And what's wild is that even with billions of those little switches, the CPU's main job really boils down to a surprisingly simple loop that it runs at mind-bending speeds. This one process is how it does everything, from calculating a spreadsheet to rendering a crazy video game. And here's that loop. It's called fetch, decode, execute. First, the CPU fetches an instruction from memory. Next, a part called the control unit decodes it to figure out what to do. And finally, the arithmetic logic unit, or ALU, executes the command. That cycle repeats billions of times a second. It's the CPU's basic heartbeat. So let's meet the team that makes this happen. Think of the control unit as the conductor of an orchestra. It directs all the traffic. The arithmetic logic unit, the ALU, that's your math whiz. It handles all the calculations and logic. And the registers, they're like little sticky notes, super fast, temporary storage for whatever the ALU is working on right at that moment. So you've got the blueprint, right? The control unit, the ALU, the stored program. But how do you actually build the thing? Well, the first attempts were nothing like that tiny chip we saw. We're talking about colossal machines that took up entire rooms, built from thousands of parts that were frankly pretty unreliable. The first huge leap forward was switching from vacuum tubes to transistors. Vacuum tubes are basically like old light bulbs. They were big, they broke all the time, and man, did they get hot. The invention of the solid-state transistor changed everything. It let CPUs become way smaller, faster, and a whole lot more dependable. But that was just the beginning. The real revolution, the one that put a computer in every home, was still on its way. The next great challenge was figuring out how to cram all those different parts of a CPU onto one single tiny piece of silicon. And that was the microprocessor. It was the absolute game changer. Squeezing everything onto a single chip meant computers could suddenly get exponentially smaller, cheaper, and way more powerful. The personal computer wasn't just a fantasy anymore. It was basically inevitable. And after that, things just took off. After transistors became the norm in the 50s, Intel dropped the 4004 in 1971, the world's first microprocessor. Then, just 7 years later, they gave us the legendary 8086. That processor kicked off the x86 family that, in some form or another, is probably running the device you're watching this on right now. So once the microprocessor was out in the wild, the race was on. The goal was pure, raw speed, and engineers started coming up with some seriously clever tricks to squeeze every last drop of performance out of that silicon. It wasn't just about making things smaller anymore. It was about making them smarter. This led to a huge debate, kind of a clash between two design philosophies. On one side, you had CISC, or Complex Instruction Set Computer. This is the x86 way. Create powerful, complex instructions that can do a lot in one go. On the other side was RISC, Reduced Instruction Set Computer. Their argument was the opposite. Use a small set of dead simple instructions that you can execute incredibly fast. It was a battle of complexity versus simplicity. So, who won? Well, this is where it gets really cool. The answer is kind of both. Modern x86 chips, which are CISC on the outside, are actually hiding a super fast RISC core on the inside. They take those big, complex instructions and break them down into tiny, simple micro-ops that can be executed at lightning speed. It's the best of both worlds. Engineers also got clever about how instructions were processed. One of the first big tricks was pipelining. Just think of it like a factory assembly line. Instead of doing one instruction from start to finish before starting the next one, the CPU overlaps them. As one instruction moves to the decode stage, a new one is already starting the fetch stage. It's a simple idea that massively improves efficiency. So what's the next logical step? Well, if one assembly line is good, why not build several? And that's exactly what superscalar design is. It's all about having multiple pipelines working in parallel so the CPU can execute several instructions completely in the very same tick of the clock. For decades, making CPUs faster just meant one thing: cranking up the clock speed. But by the early 2000s, engineers started running headfirst into a hard wall. A wall made of physics. A headline from MIT Technology Review really captured the mood perfectly. Moore's law is dead. Now what? We were still able to cram more transistors onto chips, but we just couldn't make them run any faster. Why? Heat and power. The faster the chips ran, the hotter they got, to the point where they were in danger of melting themselves. We'd hit a dead end. The industry had to make a huge pivot. A new idea took over. If you can't go faster, go wider. This led directly to the multi-core processor, the idea of putting 2 or 4 or even more complete CPU cores onto a single chip. And this was a fundamental change in strategy. We went from instruction-level parallelism, using those clever tricks to make a single task faster, to thread-level parallelism. Now you had multiple cores that could work on completely different tasks at the exact same time. This is really the birth of the modern multitasking we take for granted. And that brings us to today. The raw race for pure speed is over. Now, the name of the game is efficiency and specialization. So where does the brain of the computer go from here? The answer is to stop asking one part of the brain to do everything. The future is about building a whole team of specialists right onto the chip. It's called heterogeneous computing. So modern CPUs have dedicated units for specific jobs. Powerful iGPUs for graphics, neural processing units or NPUs built just for AI, and crypto accelerators for security. It's all about using the right tool for the job. I mean, think about that journey. From a theoretical idea about storing instructions, to room-sized machines, to a single chip that changed everything. We built these multi-core giants, and then we taught them to be specialists. For 70 years, we taught these silicon brains how to calculate. Now, with things like NPUs, we're teaching them how to learn. So the real question isn't just what's next for the CPU, but what massive problem is it going to help us solve next?